Good afternoon, everyone. This is Dilip Khatri. I'm a structural engineer based in Las Vegas, Nevada. I thank you for joining this report number 2 on the Champlain Tower collapse. For those of you that may have missed report number 1, there's a link on the next page to help you find it. This is my second report on this unfortunate event, and we'll be focusing on 2 areas of concern here. I did get a set of the drawings. I've been looking that over, and also I have found photographs which show evidence of steel corrosion, concrete corrosion, and we'll be discussing those 2 topics in this report. Here are the 2 links for the 2 previous postings. One is report number 1, and the other one are just some site observations that I made on my visit to the location. So as an introduction, I want to be clear on exactly what I'm presenting. I am not working for any particular organization here other than myself and my company. I don't represent any government agency. This presentation is for information only based upon my experience and education, having been in this industry for over 39 years. And I'm providing my field notes from my first site visit on this project on June 26th, 2021, clarifying this as report number 1, as there will be subsequent reports to follow. So new information that I found were the plans. That's the biggest piece of information, but I also did get the entire file from the city of Surfside. And from the building plans, the building is a flat plate concrete diaphragm, but it does have beams. And that is important to note, and you'll see when we get through the technical analysis that the beams create a one-way slab effect as opposed to a two-way slab effect. And I'll explain that as we get into the deep dive that we're going to be getting into. The failure observed is still a gravity load collapse. I don't see any evidence to change that conclusion. I don't see any evidence that has changed my position on no lateral force event. The age of the building is 1980, and there are a lot of evidence to support the effect of steel corrosion on the rebar and the concrete failure. And we will get into that in today's report number 2. So in today's report, there is a lot to talk about, a lot of material. So I've decided to obviously piecemeal it and keep it as short as possible, although I think this will still be over 15 minutes, but I definitely keep it under half an hour. There are 5 major topics that will be coming up in subsequent reports. In today's report, we're going to focus on only one topic, which is the corrosion on the steel and the concrete. I'm also preparing a footing analysis. The foundation consists of reinforced concrete driven piles, and with a concrete pile cap, we'll be looking at that. And then the column to slab connection, the shear and moment rotation analysis for base settlement, and the effect of the foundation rotation on upper level moments and shears. Those topics 2, 3, 4, and 5 will come in separate reports. Today, we focus on only one topic, the corrosion on the steel and the concrete, which is a very deep topic. There's a lot to discuss there, and you'll see some information here which will shed further light on the cause of the collapse. This slide is from the Google Maps. It's a 3-dimensional view of the tower prior to the collapse, and you can see here that the roof condition is in very poor shape. There is literally no drainage on this roof. It is designed with a system of parapets, and the drainage system clearly is not working. You can see the staining on the roof. There's water ponding. That might work in California, Nevada, or Arizona where there isn't much water. Even there, it's not a good idea. But clearly there's a design flaw here because the roof is clearly not performing drainage-wise. Secondly, the stain lines show us that the water sits up there for a period of time and is likely damaging the roof and then leaking through cracks in the roof. You can see the evidence very clear. We'll take a few zoom-in shots here, and I'll explain the relevance of this. This is a close-up shot of the roof. You can see the stain lines very clearly. The water saturated the concrete roof and has likely seeped in through the roof system and will be damaging the rebar and the concrete for many years. You'll see a dashed line across the screen there, kind of shaped like an L and two arrows. The arrows are pointing to the portion of the building that collapsed. So everything on the top of the diagram, above the arrow line, above that dash line, and especially where I've circled, there's heavy saturation on the roof, heavy ponding, and that was the area that collapsed. And the reason this is relevant is that water seeping in through reinforced concrete will damage the rebar over a period of time. It will cause the concrete to spall, and this reduces the effectiveness of the reinforcement in the structure. And this entire structure is a reinforced concrete building. And so we're going to discuss one topic today called bond strength, which is the bonding of the steel to the concrete and how that's compromised when you have corrosion. This slide is taken from the plans. It's on a particular sheet, which is Section 6, Waterproofing and Damp Proofing, Article 1. It says all ground slabs to receive approved admixtures at mixing plant in quantities as specified by the manufacturer, and B, flashings, etc., as set out in roofing and sheet metal. Now, I understand this is 1980. The standards were a little different back then, but clearly this is very inadequate. This is very, very inadequate set of specifications for waterproofing. And I couldn't begin to tell you how many things are missing here. My fellow professional engineers and architects working in today's environment, I think, can see the deficiencies here, but this is, by and large, very incomplete and doesn't address the roof. I mean, just putting down etc. is really a very lousy way of specifying drawings, because what does etc. mean? There's no roof membrane specified. There's no water protection. So everything starts from the drawings, and as I said in the previous slide, the design is deficient for sure as far as roof drainage, but there are many other things missing on these plans, unfortunately. And so I want to start the discussion here by first giving a little explanation, technical explanation, on what we mean by bond stress. So here, my sketch shows a block of concrete with one reinforcing bar embedded in the concrete. Embedded means that the rebar was placed there and the concrete was poured around it. That's a cast-in-place rebar, as opposed to a post-installed rebar or bolt, which involves epoxy, and that's a separate topic. But here, this is cast in place. So the rebar is there, the concrete was poured around it, it cured, and we have a dimension here of roughly 12 inches for my little small example. The rebar is assumed to be a number 4 bar, which is a 1/2 inch diameter. That's on the next sheet. And as we apply a tension force on the rebar and try to pull it out of this block of concrete, the resistance force is going to come from the friction, what we call bond stress, between the rebar and the concrete. You can see the arrows there, and F bond is the bond stress. So in my example, we're applying a tension force and we're trying to pull the bar out of the concrete. The transfer of stress goes from the tensile stress in the rebar through the skin friction between the bar and the concrete. In this calculation, we're calculating what that skin friction stress is. So the bar diameter is a number 4 bar, which is a 1/2 inch diameter. It has a radius of 1/4 of an inch. In this sketch, I'm showing visually in 3 dimensions the rebar embedded in the concrete. You have the length of the embedment, you have the tensile force pulling on the rebar, and I have a coordinate axis system. So the bond stress is developed along the circumference of the rebar on the y-axis in the diagram. So those arrows, those half arrows, are the skin friction that bonds the steel to the concrete. And here are the calculations to calculate the bond stress. I have the previous page up there in the top left-hand corner. So we have the bond area, which is the circumference, 2 pi r, times the length of embedment. In my example, the embedment length is 12 inches. For a number 4 bar, the radius is 1/4 inch, so we calculate the circumference, which is 1.57 inches, and the bond area is 18.85 square inches, which calculates the tensile stress in the rebar is 50 ksi. That's 10,000 pounds divided by the area of the bar. That's to give us an idea of the magnitude of the stress in the rebar. The bond stress is 10,000 pounds divided by the area of contact, which is the circumference area, the surface area of the rebar in contact with the concrete. And that is 10,000 pounds divided by 18.85 square inches, which gives us about 530 psi, or half a kip per square inch. And another way we measure it is per foot of embedment. So that's for a 1 foot embedment, that's about 10,000 pounds per foot. So in this situation, the bar is almost stressed to its yield value. The yield value is 60 ksi for a grade 60 steel, which was what was used in Champlain Tower and is used pretty much across the board for all concrete buildings. So we're going to take note of this number, and then I want to show you what happens to these numbers once we have corrosion and we have loss of contact area. In this sketch, I'm showing schematically what happens if we have corrosion. Corrosion was what eats away the concrete, and it exposes the rebar. You can see my arrow down in the lower right-hand corner that red line is showing under my assumption that portion of the concrete were to be corroded and it would crack and fall off and the bar would be exposed. So you would lose that contact area, so your bond stress is going to go up because your bond area is gone down, and your rebar is going to lose surface area or its diameter because of the water eating away at the rebar. And this is just shown here schematically, and we're going to run some calculations. And here we run some calculations with some assumptions. I do a 25% assumption loss of contact area. So in other words, A prime at the top line is calculated 0.75 times the original contact area. So we're somewhere around 14 square inches. And then the next line is a 50% loss in bond area. And that's A double prime, comes down to about 7.1 square inches. And the bond stress goes up quite dramatically. You can see F prime bond area stress is about 700 pounds per square inch. We started at 500. If we have 50% loss, the stress jumps to 1408. And on a little graph there, you can see at 0% we're at 531, then 750, and then we're at 1400, and the red line goes up. And if we were to have 100% loss, we would have no bond, and the rebar would pull out. That's the danger zone. And these are some calculations to express and show the increased stress due to corrosion. In corrosion, we're losing the bar diameter. So here we start off with 1/2 inch, and you can see the red line shows after some corrosion, the eroded new bar diameter. So I've made some assumptions here. With a 10% loss of bar diameter, we would be at 0.9 times 1/2 inch, or 0.45. The radius would drop, and the area, effective cross-section area, goes down. And these are three calculations: 10%, 20%, and 50%. And you can see at 50%, we're barely at 0.05 square inches of effective steel area. So these are the numbers. At 10%, our steel stress jumps to 62.9 ksi, which is above the yield stress. The yield stress is at 60, which means that at this point, just with 10% loss of steel, we're already yielding the steel. In other words, the steel is permanently deforming. If the steel is permanently deforming, that means that the slab is cracking and you're getting deflections that can never be fixed. So just with a little bit of corrosion, I would consider this fairly small level of corrosion, your rebar is now exceeding its yield stress. With 20% loss, we're well above the yield stress. We're close to 80 KSI, which means that the bar is now seriously deforming, meaning that we're getting deflections that can be seen. We're getting cracking in the building. And at 50%, we've literally failed the bar. The bar has cracked at this point. It's not going to go to 200 KSI. It's going to crack. It's going to crack somewhere, you'll see it on the next graph, somewhere over 80 KSI. Before it reaches 100 KSI, it's going to fracture. We call that the fracture strain. And so here's a sketch graph. On the vertical axis, we have the tensile stress in the steel, my number 4 bar. On the horizontal axis, we have the percentage loss of steel diameter. And 10%, 20%, and 50% are graphed here. Once you pass about 30% or less than 30%, it really doesn't matter because the bar has fractured. You're not going to get over 100 KSI stress on that rebar. This is not a super high strength bar. This is a standard 60 KSI rebar. And so why is this important? Because every concrete building in the world depends on bond stress, not just in Florida. In the world, all the reinforced concrete structures that we have, not just buildings, but bridges, everything made out of reinforced concrete depends on this principle. If you don't have effective bond, your structure is going to fail, and it's going to fail catastrophically. The important note here is the structure will give you warnings. You will know in advance that it's cracking because the steel is going to yield. By yielding, what we mean is the bar is deforming in such a way that the structure, the concrete, is going to exhibit very serious cracks to tell the observers, not just structural engineers, but people who live there, the building is screaming to you saying, I'm about to fail, run away. That's the way it's designed. It's designed to actually do that. It's in our codes that we want the building to exhibit structural cracking. So in this little example, I hope I've illustrated the corrosion effect on a very small scale. Now let's jump back to Champlain Tower and take a look at what was happening. What were the warning signs? There is an abundance of evidence that this building exhibited structural cracking for many years. This is an excellent report by the engineer of record, the structural inspector. I have these 2 pages here. We're going to zoom in here and take a look at it. And I'm just going to summarize it for you on this one slide. There were plenty of warnings to the customer, and the engineer had warned them in 2017, 2018 that they need to take care of this. So here you have photographs from the structural engineer who inspected it in October of 2018, and look at the cracking here in the columns in the parking garage. This is screaming to you. It is screaming, I'm about to fail. I'm about to collapse. That's what these photographs tell me. There's no if, ands, or buts about it. This is a dangerous situation. The building should have been condemned and red tagged. And then look at these cracks on the top side of the garage deck. Look at we were talking about spalling. Here you've got so much spalling. You can see the concrete cover has deteriorated. The bars are exposed. I don't know what to say, folks. I mean, the evidence was there. It was so clear, so obvious. I do this for a living, and I have buildings that are in similar situations where I have given similar warnings. This is not the first building I'm looking at. I've done this for close to 4 decades now. And it's just screaming to me when I look at this that, hey, I'm in trouble. The building is telling you, I'm in trouble. You need to get out. Many owners elect to ignore these signs, and they do what's called epoxy injection. They inject these cracks. You can see it in the lower left-hand side, and that doesn't do much of anything other than temporarily stop the water. It does not deal with the corrosion. It does not stop the corrosion. What it does is it prevents the water from damaging your car. And my response to that is, big deal. So what? I have so many investigations that I've done where I've seen these epoxy injection ports done, and owners have spent a lot of money. And there are some, not everyone is an unscrupulous contractor, but there are some contractors out there unscrupulously will sell this as a structural repair, and it's not. So the first takeaway here is that if you're having these kinds of damages in your parking garage, you need to take note and you need to do something about it on a serious level. And you need to listen to your fellow engineers, your consultants, the people that you've hired who are the experts in this field. You need to pay attention to what they're saying. So here's the signature page for Mr. Frank Morabito, professional engineer, member of our society, a fellow professional, a colleague. And look at his language. He says, understanding that required maintenance that is needed to properly maintain this existing residential property. It goes on to say, MC is available to further discuss the recommended repair and how it coincides with the owner's desires and constraints. We look forward to working with you in maintaining the structural integrity of the Champlain Towers South condominium. He's offering his advice and recommendation and saying, I want to work with you to make it happen. I don't know what else a structural engineer is supposed to say. I can assure you my language would have been much stronger. Much stronger. This is very mild and polite. I would have been much more, I would say, vocal is a better word if I had a situation like this, which I do, by the way. I have situations that are like this. It's very unfortunate. The owners had this in their file and they didn't do anything. So the scope of this problem exists for many decades. We've had erosion, corrosion problems for a long time. This is a slide taken from a presentation I did in 2016 for the Structural Engineers Association. This topic is not a new topic. This has been around for a long time. I just took these slides out of my last presentation. I've done this presentation for various other associations, and I just wanted to bring it to your attention that this is nothing new to us as structural engineers. In fact, ASCE, American Society of Civil Engineers, has issued a report to the government regarding the condition of infrastructure in this country and given it a grade rating of D for David, just one notch above an F. And that's pretty realistic. We've got this problem going on across the nation, not just with this building, but with many bridges that are outdated and old. This is an example slide from one of my projects. You can see the corrosion. This is in a subterranean parking structure with a deck. And look at the level of corrosion. Look at the concrete has spalled away. You can see the rust on the rebar. And this is a critical connection. This subterranean parking is supporting multiple stories up on top. This is happening in Southern California at one of the jobs that I was working on. I have many slides like this. And I just want the audience to know that this is happening not just in Florida, but across the country. In fact, it's happening in any building out of reinforced concrete. This is an issue, particularly those of you that are near the coast that have exposure to saltwater environments. And when I say coast, I'm not just saying East Coast and West Coast. I'm talking worldwide. There are so many reinforced concrete buildings near the ocean. Each one of them has a problem like this, especially if they're over 40, 50 years old. So I thank you for attending this report number 2. I've gotten many comments back, thoughts and likes. I appreciate all of them. I try to read all of those comments that are made, and there are additional reports forthcoming on the other topics that I mentioned at the beginning of the report number 2. There's more to come on this. This is a big topic of discussion. I thank you again and wish you all a lovely day.